Now, okay, so most of you watching at home, there's nothing wrong with the audio. My voice really does sound this bad. Okay. Hopefully hydration helps. All right, so let's see. Okay, so when I taught the last section, 5.1, most of you were not here because I let you leave class to study for that dang analysis midterm.
Thank you.
So, should I do that again on Wednesday?
No.
Or next Monday? I'll keep that in mind. Now, there was class anyway, as well, I guess Haley and Abdullah sat through.
That was a great class.
It was fun. Yeah, and I have to talk about zombies. So,
Yeah.
now, have any of you who were not there watched a video for that yet? Probably not. Or is it Atlanta happened and all that? So, please do. It's okay if you haven't watched it yet. It should not affect things for this next section, 5.2. But before you jump into the homework for chapter 5, you should do that. I know it says on the site, chapter 4 homework due Wednesday. I know a lot of people are thrown off from the Atlanta trip, so, well, I don't really care much about due dates anyway, so if you need more time, just take it. So, whatever you need to do there. Alright, so, actually, this is a relatively short chapter, anyway. Oh, I have homework to give back. Let me take care of that real quick.
Definitely two.
We all do. We all do.
Abdullah's the only one actually worried. Nika's just like, whatever.
Well, I thought, like, do I have some? Forget that.
You're brown.
I'm brown. So right?
Oh my gosh, no, I just love when Teresa, like, we got that picture and you were like sitting in the back or something like that. You're like, how dark am I? And she's just like, the darkest or something crazy.
By far.
Yeah, we're just,
Because it has like zero light.
Yeah.
I haven't received homework from everybody, but those that I had on hand for,
yeah.
this is homework 2. Oh. Abdullah, I have yours. I somehow forgot to grab it out of my bag, but it's right in my bag.
Okay.
Well, you don't have class next period anyway, so
Yeah.
you get it done. So, great job, everybody.
I have that and I completely forgot to give it to you.
Okay.
I'm so sorry.
Well, as soon as you get it to me, I will grade it too.
Okay.
even remember this homework.
Yeah, it was quite a while ago.
I'm probably the only person who turned in homework free on time.
Yeah.
Yes, that's true.
Yeah.
So, it's
Well, when was homework free due? About the 19th, I guess,
Yeah.
which was the day of the analysis midterm. So,
yeah. 4 is due tomorrow.
Just
or
halfway
day after
When?
tomorrow.
yeah.
And we haven't even started it, so.
Well, we're all over this semester, so just
How many homeworks do we have total by the end of the semester?
6, one for each chapter.
Oh, so we're not even halfway there yet.
That's right.
Like almost there.
I'm halfway there.
Almost
Almost
halfway.
The thing is, we're going to finish chapter 5 on Monday.
You realize Thanksgiving's in like 3 weeks.
I want to turn in 4 and 5
Yeah.
before Thanksgiving.
And then there's chapter 6, which takes up the rest of the semester.
You got 8 homework.
And at some point, we might just fizzle out. But so we'll see what happens with homework 6. It might either be abbreviated or just ditched altogether because
No.
we'll see.
6 is a bad number, you know.
I know.
Yeah, and
It's hard to
If
weigh
it's
6
homework,
homeworks, 5 isn't even, you know. everybody's-
no, 5 is not even.
Yeah, but everything's weighted equally, so-
No one asked you, Abdullah.
Like,
We start from
0.
0.
Yeah, it's not like 16.6.
That's what I meant.
It starts from
Even
0. 0,
weight.
1, 2, 3, 4, 5.
Yeah, so 5 is not even.
Okay. Anyhow, let's get something done before y'all have to run off to analysis. Now, I'm actually not going to jump into the notes immediately because one thing that, I guess one of the reasons I like differential equations is because there's a fair amount of linear algebra involved. But in a book at this level, it's got, the author will kind of assume that you already know the relevant linear algebra, and chances are you guys have forgotten it, or knowing 326 as it is, never learned it in the first place. So, we're actually going to start with I'll start with a linear algebra lesson to make sure everybody's up to speed on that, and then what we see in the section, you'll be better able to work with. Okay, so I guess what I do in a lot of classes, including this one, is fill all the holes that were left by 326. Okay. Although it seems I can make just about any class about linear algebra. Actually, there's a well-known saying about that mathematics is the art of reducing all problems to linear algebra. Well, because once you get to that point, then it's a lot more straightforward. Okay, and in particular what we need for this section are determinants and especially inverses. Okay. So, alright, so first, some basics. 'Cause in this section, 5.2 we're about to do are cases where we have a matrix and we need to compute its inverse. So satisfies A times A inverse, or A inverse times A, doesn't matter what order you multiply in this case, is, no, that's totally wrong. Is the identity matrix, ones are the diagonal, zeros everywhere else. Now, I think it's in this section, certainly for homework for this section, you're going to be dealing with small matrices. What we like to have is a formula, preferably, for the entries of the inverse. So everything I'm going to do in this section is completely impractical for a large matrix setting, but for small matrices, it's okay. So to get to a formula, we can use what is called, Cramer's rule, which says the following, because also Cramer's rule is useful beyond inverses. It's useful for solving systems of linear equations. So Cramer's rule says that the solution of AX equals B is given by this formula. Each component of the solution X is the determinant of a matrix I'll call A sub J divided by determinant of A, where the matrix A sub J is a matrix you get by replacing the J column with B. So if you compute all these determinants, you can get the entire solution. Now, this is the sort of thing that never comes up in a numerical analysis setting, because to compute these determinants, very expensive. But for matrices like 3x3, 4x4, that size, at least, especially if your matrix has a nice structure to it, you can at least come up with analytical formulas for your entries. And for theoretical interest, that's often helpful. Okay, now, so for A inverse, I can write A inverse in terms of its columns, which I'll call and each column of the inverse is a solution of this system of equations. A times the ith column is equal to the ith column of identity. So you have all zeros except for a 1 in the ith position. And this just comes, so that just comes from this equation. A times A inverse is identity. That is a matrix equation. If you look at the matrix equation, one column at a time, it's exactly this. So what we could do is, if you want to get each column of the inverse, you can use Cramer's rule to get that column. So to get each entry, so actually, what I could do is now drill all the way down to getting one entry at a time. Actually, I'll leave that board up a little bit.
Yeah.
That's not worth leaving out.
Not anymore. Not like it.
What today? Lucky day.
Because she didn't draw all the stuff on there, so it's not shocking.
Yeah, this is an unthemed class. Okay. Well, could have been very entertaining and painful. Okay. So to get the ij entry of A inverse, well, that would be equal to the determinant of okay, I'll call this matrix and Aij that's a matrix obtained by replacing column I of A with EJ. Now, so really, what happens is, based on the properties of determinants, what you have is a determinant of the matrix obtained by removing column I and because EJ is all zeros but it has a 1 in a jth position, you're removing row J. Now, what the other thing to keep in mind is, if you have a matrix and you interchange rows and columns, every time you swap two rows or swap two columns, yeah, it changes the sign. So I need to correct this, multiply this by -1 to the I plus j in order to get the sign correct. So this leads to a well-known formula for the inverse. So, A inverse can be described as 1 over determinant of A, which of course has to be non-zero, times what is called the adjuvant. Now, what is the adjuvant? Is a transpose of another well-known matrix, which is called the cofactor. Cofactor matrix. And so Cij, so the definition of a cofactor matrix is -1 to the I plus j times the determinant of A with row I, column j removed. Okay. Now, I should mention the adjugate matrix used to be called the adjoint. And some older books will still call it that. Well, of course they will still call it that forever because they're old. It's not like they're going to change. That'd be cool though. If old books automatically updated to new terminology. Well, anyhow.
Now they will.
So, because adjoint is also used to refer to a transpose. Now it causes confusion. So now we just call it the adjugate. Now, one thing I want to point out here, notice here I say determinant of A with row I, column j removed. Here I have row j, column I. That's why I have this transpose here. So that's a very important detail. Okay. So, in this section 5.2, when we get to a point where we need the inverse of a given matrix, at least for purposes of homework problems and such, or any examples that I'll do in class, well, for 2 by 2, there's a formula for the inverse that's very easy. And this just reduces to. Say 1 over determinants. And then these cofactors, you're taking out a row and a column. So what that means is, if you take out a row and a column of a 2 by 2 matrix, all you're left with is a number. So it just turns out to be that. So you don't even need this for a 2 by 2 case, but as soon as you move up to 3 by 3, then this formula becomes useful. Okay. So if you have a small matrix, you want the inverse. If you're going to do it by numerical analysis type means, you'd be doing Gaussian elimination and all that crap. And if you have functions as your entries, that's incredibly tedious. But this would be a good way to go for a matrix like that. And when we get to a certain point where we have a 3 by 3, as an example, you'll see this process illustrated. Now, Kramer's rule actually, it seems like a pretty straight formula. This ratio of determinants to get the solution, but it can actually be proven without too much difficulty. I won't do it here. In terms of the properties of determinants. So for instance, like we mentioned earlier, if you swap 2 rows or 2 columns, the matrix of sign changes. If you multiply a row or a column by a number, it scales the determinant by that number. If you add a multiple of a row to another row, like in Gaussian elimination, it doesn't change the determinant at all. which seems kind of counterintuitive, but it's true. So all those properties like that can be used to come up with Cramer's rule. Okay. So this is the linear algebra that you'll need in this section. Okay. Now, as for how we're going to use this, yeah. Now you've done changes of variable before in different contexts, like substitution and integral, or change of variable like to polar coordinates, spherical coordinates, cylindrical coordinates. So usually for derivatives or integrals. So now, what happens if you make a change of variable like that in in a DE or a system of DE? So the purpose of this is to get a simpler system to solve, or maybe a simpler system to understand. Like if you have a DE where your variables are x, y, z, like Cartesian coordinates, maybe the system is easier to solve if you switch to spherical coordinates. So if you want to change coordinate systems, you know how to do that for a point or an integral. But how do you change, if you have a given system of DE, how do you transform it to an equivalent system of DEs in the new variables? So basically using tools from calculus. So I'm going to illustrate using a single DE. So x prime, it's big X and little x. So the idea is everything here depends on t. T is your independent variable. But what we're going to do here is change our dependent variable. So we're going to change to a new variable y that also depends on t. And a function f, it can't be just any function. It has to be what's called a diffeomorphism. Now, in modern algebra, you learn about homomorphisms and automorphisms and isomorphisms. So this is a morphism for calculus land. So f has to be 1-to-1 and onto. So that means it is invertible. And it has to be differentiable. So that's where the diffeo part comes from. And so because it's 1-to-1 and onto, we have g equals the inverse of f. And another condition of a definition of diffeomorphism, the inverse is also differential. Now, you may have seen that the derivative of an inverse function is related to 1 over the derivative of the original. So derivative of the original cannot be 0. But if it was 0, it would not be invertible anyway. So all that works naturally. Okay. So if x prime is big X is little x, our goal is, what is our equivalent system for y prime? So here's how we'll do this. We have y is equal to f of x if and only if x is equal to g of y. So we can look at this from whatever point of view we need, whatever is most convenient. So I have, because x prime is big X, little x, I can write all of this in terms of y. So I'll have g of y, the whole thing prime. Now that is not just g prime of y. It's not as simple as that. So I'm just replacing x by g of y throughout. Now, if I want a derivative of g of y with respect to t, it's not g prime of y. What do I need to use to differentiate that? No.
The inverse.
Well, we don't need to use the fact that it's an inverse yet.
So y equals f of x, right?
Because keep in mind, g is a function of y. Y is a function of t.
Well, f of x is a function. Well, y equals f of x, right?
Right, but we'll stick with x equals g of y. Now, this is x prime, dx dt. So, but now replacing x with g of y, but y also depends on t. So how do we carry it? So if you want, you can write it this way. I'll write this x of t, and this is g of y of t. So how do I work that out? What rule do I need to use?
Like chain rules.
Chain rule. So what would that give me?
G prime y of t.
Depends on what times the derivative of y.
Y.
Yeah, times y prime. And this is good because we want an equation of a form y prime is equal to something, and now we have y prime involved here. So we have g prime of y prime is big X of g of y. So now I'll just move g prime of y to the other side. So y prime is, I'll write it this way, g of y inverse big X of g of y. Now, I could write it as 1 over in this case, but eventually we're going to talk about systems of DE, where g of y will no longer be a function, it will be a matrix. So this notation will be consistent. Okay.
Why is it just g of y and not g prime of y?
Oh. Yes, this is supposed to be g of y. Okay.
Wait, what did you just fix?
This has to be a prime.
Okay.
Yeah, like over here. Okay. Now, what I'm going to do is I want to express all of this in terms of f, which I can do using the fact that this is that g is just f inverse. Okay, now g is f inverse, so that means that g prime of y is 1 over f prime of f inverse of y. So that's the rule for inverse function. If it was a vector value function, instead of 1 over, actually I shouldn't write it this way. It works now, because we're talking about a single d, but more generally, I should use this notation for a case where f prime is actually a matrix. Now, if I go back to my DE for y prime is g prime of y inverse big X of g of y. But I have g prime of y is the inverse of this. So if I take the inverse of the inverse, where does that bring me?
Back to your original question.
Back to the original. So it's just going to be f prime of f inverse of y, big X of f inverse of y. So this is my transformed system of DE. So if I have x prime is big X of little x, and I say, well, y is f of x, I'm making a change of variable, then this is a transformed system in y. So that's how you transform a DE. When we make a change of dependent variable. Now, I'm going to find some notation to condense all this. This is f subscript star of big X that itself is a function of y. And this is called the push forward of X by f. And actually, it seems like a strange term, a push forward. There is a pull back. So there's push forward and pull back mappings. We just only need to push forward in this section. Now, so it's a way that you describe big X, because big X is a function of little x. But you want to describe what is big X as a function of y. It's this. So what happens is this DE is equivalent to the push forward of X applied to Y, which I'll abbreviate as big Y of little y. So in other words, big Y is my shorthand for push forward. So this is the equivalence. Okay. Where, well, where I'm just repeating the definitions for that. As I assume you're emphasizing this in your notes, all these central ideas are in this box. All right. Now, let's.
Excuse me.
Okay.
All right. Now, so now we know how to transform the DE. So the next question is, if you have a solution to your original DE, how's it relate to solutions of the new DE? And it turns out there is a simple relationship. Okay. Well, I'm glad this candy isn't going to waste. I didn't think it would.
Already ate $1 million of it. Now I have like I ate 3 grams, 300 grams.
Okay, so if alpha t in solution of the original system, then f of alpha t, which I'll label as beta t.
Is this gonna be a little X prom?
Yeah.
Okay.
Solves the transform system. So at least there's a simple relationship between solutions of the two. Now, to just help you see why that is, let's look at beta prime of t. Well, that would be f of alpha t prime, and for that use a chain rule, which is f prime of alpha t, alpha prime t. But alpha prime solves the original. So that would be big X of alpha t. But alpha of t, is f inverse of beta t. So we can use that in here. So that's f prime, f inverse of beta, x, big X of f inverse of beta. But all this is the push forward of f of big X applied to beta. But the push forward, that is big Y beta. So it solves it. Okay. So beta, in fact, does solve the transformed DE. All right. Now, everything that I've been doing here is for a single DE, but most of the time we're talking about systems. But everything I've done here applies in a very straightforward way to systems. It's just easier to do with manipulations when you're talking about a single DE. You're just doing single variable calculus. So as long as you just use the appropriate notation for higher dimensions, everything applies. And actually, really, that's what the linear algebra does. It makes it so much easier to describe everything, single variable and multivariable, all in the same way. Doesn't matter of what multiplication are you doing. Are you doing regular multiplication or matrix multiplication? Okay. So what we really care about is systems. So really, it's not going to look much different at all than what I've just been writing. I just need to use vectors wherever appropriate. So x prime, big X, little x, where x is now a vector in Rn. Okay, so these two systems are equivalent where y is now a vector valued function of x, so really it's a vector field. That's why I was using vector symbols all over the place. And your new vector field y is the push forward of big X. Oh.
It's just the power.
I know, but it's like if this broke, then that'd be bad. Okay. Where the push forward is defined in the usual way. So it's f prime of f inverse of x of y times big X of where what's happening is now f prime is a Jacobian matrix, and the multiplication that's happening of f prime times big X right here, well, big X is a vector field now. So this is matrix vector multiplication to give you a new vector, which is big Y. Multiply. Oh my God.
What did it say?
What did I say before?
Uh-huh.
Multiplication, like
Multiplication.
I was just curious.
Okay, so I'm going to leave that up there so it can be immortalized on video forever. Multiplication.
Ah, I was just curious.
Yeah,
I
well,
like it.
Alexandria was actually pronounceable. I figured it was worth.
It'll become a word one day.
subtraction.
Well, seeing the decay of the English language that's happening all around,
That's what I'm saying. It will become a word one
especially
day.
your generation that can't keep it. It is straight, and many other things. All right. Okay. If I'm gonna be suffering up here with my voice in the state that it is,
You deserve it.
I think so.
You should have let me run and grab some coffee or something before.
Oh. Okay. Okay. Now, so actually, when it comes to solutions of one system of DE versus the other, we actually have an if and only if thing going here. So, alpha t solves the original system. And then beta t, which is big F of alpha t, solves this system if and only if big Y is the push forward of big X. So the way you would show the this direction, where you're assuming this, and you show that that the betas are solutions, that I already did for a single DE case. But if instead you are given this, then you can show that big Y of any little y is equal to the push forward of big X applied to little y for all little y. So that's why it's if and only if. So the push forward of a vector field is the only mechanism for getting this kind of equivalence of two different systems of DE. Okay. Now, some terminology. Okay. Big Y here as defined to be a push forward of another vector field. So this is the transformed vector field. And these two systems, big X prime is big X little x, and Y prime is big Y little y. We say these two systems, if they're related in this manner, are differentially equivalent. So I'm going to underline these terms so that they're emphasized in your notes. That'd be an example of a homework problem. Show that these two systems are differentially equivalent, for instance. Okay. And this will be a flashback to either modern algebra or discrete for y'all. The notion of two systems being differentially equivalent is an equivalence relation. Anyone remember what it means to be an equivalence relation?
It has to satisfy three properties.
Which are?
Transitivity, symmetry, and reflexivity.
Yeah, and you listed them all backwards.
Those were just the order that popped in my head.
Yep.
Reflexive, symmetric, and transitive, right?
I
Yes.
just said that.
Yes. Same properties listed forwards. Yeah.
Yes, in the right manner,
Right.
The point is, you're just mad because I said them before you.
Oh.
I finally got something right.
right? Why would it
It's the only thing I'm good at.
Okay. Yeah, and actually that is a homework. That's one of the exercises that shows the equivalence relation. I did not assign it though because I didn't think it was all that interesting.
But, so you're saying that they're differentially equivalent when we can prove both ways of the economic.
Well, it's just that. Well, it's not really conditioned on that, but it's just just to push forward. Operation on vector fields happens to be an equivalence relation. So that the only interesting property of this is a transitivity property. If these two are equivalent, and then y prime is equivalent to some other system like z prime is big Z and little z, then that system is also equivalent to this one. Just so it carries over through any number of push forwards.
So you're saying it's show that it's differentially equivalent. What do we need to do? We need to show that the transform vector field is actually the push forward.
So really, so the way you would do it is, or for reflexive is trivial.
Right.
Symmetry, show that the push forward from y back to x, so it'll be like g star, big X is g star of y. You would show that big X actually is equal to that. And then the transitive would be like, if you took two push forwards, like x to y and then y to z, and composed them together, then that's the same as a push forward from x to z directly. Bless you. And you can see why that's true, bless you, because what would you be doing? You'd be multiplying Jacobian matrices.
Right.
Well, that's a chain rule. So that's why it works. Okay. Actually, it does seem like, well, there's some non-trivial manipulations, but I thought there were more interesting problems to give. So I didn't give that one. Dang it. Okay. How much time do I have left?
4:25.
Okay. All right. Well, I'll tell you what. I'll just, well, there's one thing I can definitely fit. So I'll go ahead and do that. And then anything else can be saved for Wednesday. Now, he's doing his Monday and Wednesday both.
For the rest
He's
of
doing
the
it like from
semester.
now on.
Every
What?
class.
For the rest
Every
of the
class
semester.
for the rest of the semester.
Like, how do you fall back for
I
a
don't
time?
know. That's what, like, when he
And-
first get talked about it, I was like,
I thought only Dr. Waters did that.
I know. The problem was like nobody was saying anything.
I was.
You were
I was the only one who had the heart to speak up and be like, hello, some of us have other stuff to do.
What?
There was nobody else speaking up and like arguing with him, like, you can't do that. And I was the only one who was like, hey, I got crap to do. I got stuff, places to go, things to do. But nobody else, everybody else is too scared of him.
Your argument should be enough.
Yeah, I find it very interesting just how scared y'all are of
I'm not.
us professors.
I'm not.
And with certain exceptions, obviously. Because when I hear my students are scared of me, it's like, what?
He made it seem like we couldn't have the extra tests if we didn't take this extra time though. Yeah.
It was like a bribe.
We
It
didn't
was
really
like,
have an option, yeah.
he was like, he said, we need the extra time.
Yeah, I
We
mean,
cover-
He pretty much said we'd be behind, like,
Yeah.
for,
He said we have to cover the extra material for, especially for the people who were taking 442 in the spring. He said, so I tell you what, if y'all stay and do this material, I'll give y'all an extra test.
yeah.
But then he's
I
gonna
know,
drop our
this
lowest.
scheduling is kind of a sacred thing because for one thing, it has to be unanimous.
But then he's gonna drop the lowest test. Like we keep the higher one and keep the final.
You guys complain a lot, just do it.
This one was like 4 weeks though.
Well, the thing is, I wonder if I'm just really.
I'm gonna throw something at you one day, and it's gonna be harder than a piece of candy.
Wait until I'm over there.
I've got pretty good hair. It's okay.
He's
What?
gonna forward it. If you tell Dr. Sugar, don't use your own email address.
Oh, I know.
Yeah.
Good point.
Oh, that clearly got Dave didn't pick up on it last time.
No, he did. He missed that.
Oh, yeah, yeah. Anyhow, okay, so maybe just one example so you guys can rest a bit. Okay, so an example of differentiable equivalence. Suppose you change a variable f is linear. It's a linear operator on Rn. So I can describe the action of f in terms of matrices. Yeah, I gotta stop soon because my throat's getting sore. So f of x is just some matrix q times x. So q is some invertible matrix. So what that means is f, big F prime, the derivative or Jacobi matrix, it's just Q itself. So what does that mean about the push forward of a vector field big X is going to be Q, so this is your F prime, times big X of Q inverse. Okay. I need to apply this to a vector y to define this. So it's just that. Okay. So now the push forward has a somewhat simpler definition because Q is a constant matrix. There's no need to plug in an F inverse of y here because you're evaluating F prime at that. If it's constant, whatever you evaluate it at doesn't matter. It's still just going to be Q. All right. So let's suppose that big X is linear. So big X of little x is just the matrix A times X. So what that means is the push forward of big X is just going to be QA, Q inverse. Now, we've seen this before, where you take a matrix and multiply on the left by something, and on the right by its inverse. This is called a similarity transformation. And a good thing about a similarity transformation is it preserves the eigenvalues.
Then it's diagonalizable.
Well, A may or may not be diagonalizable, but and that takes me to my next point, which, considering the time and the state of my voice, is my last point. So one goal you should have is, if you have a linear system to start with, you want to transform it into something differentially equivalent. You choose F, which means choosing Q, to reduce A to a simpler form, like maybe Jordan form. Now, if A is diagonalizable, that means that your push forward matrix is also going to be a diagonal matrix. So, and the thing is, even without doing all this push forward differential equivalence stuff, if you're only talking about linear systems, you can show directly that two linear systems are differentially equivalent if you just take your matrix and do this to it, because all it is a change of basis. So here we have some guidance on how to choose a helpful transformation F, because the goal behind doing anything with related to differential equivalence is you want to take your system and transform it into a simpler system. So if you have a linear system, you want to reduce it to its Jordan form or something. Also, if you do reduce it to something triangular, that would help too. That would simplify it. Dang it. Now, what if you have a nonlinear system? If you choose a linear transformation that approximately reduces it to a Jordan form, like maybe it would reduce the linearization, which I talked about last section, to a simpler form, and that also would help. So, because if you're able to reduce it to a Jordan form, that means that some of the equations will decouple. And that's very important, because then you can solve them independently of each other. If A is diagonalizable, then this kind of transformation will separate all the equations. And also those equations would be very easy to solve. It'd just be straight exponentials. So that's really the goal behind all this is, now that we know how to transform one system to another, if we see what happens in special cases like its linear case, then it gives an idea of how to choose transformations that will be advantageous to us. Now, what I'll do on Wednesday is look at this from a different point of view. Suppose you have a system that's in Cartesian coordinates, x, y, and z. If you want to transform that to polar or cylindrical or spherical coordinates, how would that go? So in cases like that where we know exactly what the transformation is, we can actually work out some details and also get an idea of what the transformed system is going to look like. And then, we'll be done with transformations, and we can finish this dang chapter on Monday. But I basically cannot even speak anymore. So, any questions about this? So we'll just deal with more specific examples of this push forward on Wednesday. Now, enjoy your 2 hours of analysis. Well, except you two.
Yeah.
I know, what's the fly?
Okay, well, I got you.
So they're like,
Oh my God, I totally forgot. Well, you guys can go, but what?
No, you can't take a whole bag. No, you can't take a whole bag. Because
Sorry, I forgot to take this part of the board.
Jana and Corwin and.
No, that's okay. I mean, I'll just leave it up.
No,
While you guys all
your
leave.
name was drawn. Whose name was drawn?
Lucy.
No,
I do Tammy. I don't even know who Tammy is.
I think you
She
should take
teaches
I have to do
on
some
Wednesday nights
you,
at 5 o'clock.
Tier, and Jana.
On Wednesday night.
I actually gave mine to someone else. I forgot, Juwan. and-
Actually,
Well, I thought you were like.
Guys.
In the Virginia or whatever.
Could y'all just
You know what I mean?
quickly scram? Because that way I'll talk about it on the board.
Fine.
I'll just get.
Sorry about that.
Big basic.
Oh, I messed up. Oh, shoot.
No, you can have it. I'll come back.
Yeah,
later.
okay.
So say pull that way, and I'm like, that's fine. I'm like, why would you push that? So it's like,
Sorry.
let's go.
Okay, sorry, I completely forgot to move the laptop to capture this. So this is all that I wrote on the board in the meantime. At least you can see it all here. So I'll just take a little time to quickly go over this again. So the specific example we're talking about, our transformation big F is just a linear transformation of variables. Transforming a vector in Rn to another vector in Rn. And when you transform a vector in linear fashion, a linear operator on a vector space, that's equivalent to just multiplying by a matrix. And you can see this in any example. So we can represent the transformation big F as just multiplying by this matrix Q. And Q has to be invertible because big F is a diffeomorphism. It must be invertible. And because it's linear, it's easily differentiable. So the Jacobian matrix of this, well, like what's the derivative of A times X? A. So what's the derivative of linear transformation, multiple variables? It's just the matrix. So the push forward is just going to be big F prime, which is a Q, a constant matrix, times big X again. So it's the same definition of a push forward we've been using. It's just the big F prime of F inverse of Y simplifies just to Q because it's a constant. And then we have F inverse of Y in here, but that says Q inverse times Y in here. So that's the push forward in the general case. Now, if we assume that big X is linear also, so big X of little x is just A times little x for some matrix A, then this reduces to this. It's just QA Q inverse. So that's the push forward in that case. It's just a change of basis. This is a similarity transformation of A, which is good because it preserves the eigenvalues. So that gives us an idea, how do we choose big F for a given system, big X? In order to reduce the matrix A to a simpler form, natural candidate is the Jordan form. Like if A is diagonalizable, then QA Q inverse will be a diagonal matrix. So it decouples all of the equations. So you can solve them independently and also solve them very easily. In the case where big X is not linear, we can try the same idea. We can look at a linearization of big X, like in the previous section, and try to reduce that to a simpler form. So when we want to use big F as a linear transformation of dependent variables, this gives us an idea of how to choose it. Okay, so that's all for today. Sorry, but I forgot to move a laptop as I was recording. So we'll just do polar and cylindrical and spherical coordinates next time to see what those transformations look like. Okay.